Hello everyone, and welcome back to the AI Research Roundup. I'm your host, Alex, and today is May 2nd, 2025. Alright, we're diving into learning to search from demonstration sequences. This ICLR conference paper came out January 22nd, so just over 3 months ago. It tackles how AI can learn planning, just by watching examples. This paper introduces a method called D-TSN to learn search strategies directly from demonstrations, even without a perfect world model. So let's visualize how D-TSN actually builds its search tree. It works in these phases. First, there's an expansion phase. Okay, here it samples a leaf node, based on path values using softmax, and explores potential next steps using the learned functions. Then, critically, there's a backup phase, where the values of the nodes get updated based on the results lower down the tree. This helps manage the search dynamically. Okay, so moving to some results. This table compares D-TSN against a supervised fine-tuning approach, specifically on the game of 24. It shows the success rate for both methods, based on different amounts of training data. Well, you can see D-TSN consistently achieves much higher success, hitting over 45% with 10K trajectories, compared to just over 21% for the SFT baseline. This really highlights D-TSN's strength in learning search effectively. Building on those game of 24 results, this table shifts focus to the ProcGen benchmark. Okay, this is more complex because the world model isn't given. It has to be learned too. So we see D-TSN compared against a model-free Q network, a model-based search, and tree QN. Looking at the bottom line, the mean z-score, D-TSN achieves 0.35, which is the highest across the board, suggesting strong performance overall on these games. Okay, turning now to the navigation task. This table shows results for both 2-exit and a harder 1-exit scenario. So D-TSN is compared against the same baselines: model-free Q network, model-based search, and tree QN. Well, on the 1-exit task, which really tests generalization, D-TSN achieves an amazing 99.3% success rate, far outperforming the others. It also has the lowest collision rate across both scenarios, showing its robustness and safety. So, thinking about how D-TSN achieves these results, especially with the dynamic tree building we discussed earlier, this figure highlights a key challenge it overcomes: discontinuity. Alright, you see two slightly different search trees here. Depending on some parameter theta, which could relate to the learned path values, the search might expand node N1 first, or node N2 first. This creates different tree structures, which can cause abrupt changes in the loss, making learning difficult. Alright, so to handle that discontinuity and learn effectively, D-TSN relies on several learnable components. This figure illustrates these core submodules. Okay, you have an encoder which processes the input state into a latent representation. Then there's a value module, a transition module which acts as the world model in latent space, and a reward module. These all work together, learned end-to-end, to power the search and planning process. So, wrapping things up, we've seen how D-TSN uses these learned components to perform differentiable tree search directly from demonstrations. Okay, the key takeaway is its ability to learn search end-to-end, even when the world model itself needs to be learned, showing really strong generalization on tasks like navigation and ProcGen. Alright, that's all for this research roundup. Thanks for tuning in, and see you next time.